Hey everybody, Mr. Piercy here with our last lesson in our topic 4 material. What we're going to be looking at today is properties of isosceles and equilateral triangles. Now, odds are you probably know a little bit about isosceles and equilateral triangles already. Uh, your experiences may be slightly different than other students have been, but in my experience as a teacher, high school geometry, uh, I recommend these students come in with some basic understanding of what an isosceles and equilateral triangle are. We discussed them previously, even in this course, about how you classify a figure by its sides. So already you probably can say, well, an isosceles triangle has to have two sides that are the same, and an equilateral triangle has to have all the sides that are the same. Well, we're going to be looking at some particular things about these, and there's images that I put here that I want to make sure everybody understands the parts of them. Now, an isosceles triangle and an equilateral triangle both have their uses. Because an equilateral triangle is considered a regular polygon, meaning it has all sides and all angles that are congruent inside of it, it actually has relatively limited use for what we're going to be doing in, in this course. Isosceles triangles can be much more versatile and wind up popping up all over the place when we're dealing with other figures in geometry. Particularly, the first thing that comes to mind is whenever we have to look at regular polygons. So if we're looking at, say, a pentagon, hexagon, things like that, well, a lot of times what we do is we break them down into their smaller isosceles triangle parts and evaluate them from the standpoint of a triangle rather than the whole pentagon or whatever the polygon happens to be. So in the images that you see, the isosceles triangle that you have here is pointing out a few things to you. Not only does it have two sides that are the same, but the one side that's not the same is referred to as the base of the isosceles triangle. It doesn't need to be at the bottom, however. One of the things that students do have a tendency to confuse is that base has to be at the bottom and that height has to be up and down, or altitude has to be up and down. Now, the one angle in the isosceles triangle that is different is called the vertex angle. And a lot of the things that we will do will come from the vertex angle. So if we were, most of the time when we're looking at a figure, if you're talking about the height, we draw it from the vertex angle. It doesn't always have to be. It just works out that way a lot, simply because the base angles wind up being congruent. The legs obviously are the same. The base is different. The base angles are called base angles because they're made with the side that's the base of the triangle. So here, we'll just go ahead and pop this up here. This, uh, we can refer to this as the altitude. We can refer to it, in this case, as a median. And we could actually also refer to it as a perpendicular bisector. Now, the only reason that I bring these up is because these are going to be things that we'll be discussing in future lessons, those particular words. In an isosceles triangle, if I draw the altitude from the vertex, it also happens to be a median and a perpendicular bisector at the same time because it actually fits the definition of all of those. So the diagram down here at the bottom, this is particularly what I wanted to illustrate. Here, in the triangle on the left, where it has angle 1 and angle 2, the base of the triangle is actually at the bottom, whereas in the second triangle, where it has angle 3 and angle 4 in it, the base is kind of that side on the right. And the reason I know that is because of the way the hash marks are indicating what segments are congruent to each other. So again, just keep in mind, base does not mean that it's going to be at the bottom. We're going to see the word base used several times for different figures in geometry, and height doesn't mean it has to be up and down. So make sure before you continue going on, make sure you have the definitions copied down and the images copied down into your notes. But let's go ahead and take a look at properties of isosceles triangles. So obviously one of the main things about isosceles triangles is that it does have two sides that are the same, but as we saw a second ago in the definitions, it also creates two angles that are congruent to each other. They're called base angles. And there's reasons for that. There's, again, one of the things that we'll talk about in a future lesson talks about how the length of a side of a triangle is related to how big the angle across from it is. So if what we're seeing here in the converse of the base angles theorem, we see that we actually have two angles that are the same. Well, if those angles are the same, the side across from them also has to be the same, and that's the converse of the base angles theorem. So one, obviously, if it's isosceles, if the two sides are the same, then we say that the base angles would be the same. But conversely, if I say I have two angles in a triangle that are the same, then the sides across from them also have to be the same, making the triangle isosceles. So here, name the two congruent angles. Well, here in the diagram that we see, segment FH and segment GH, those are the ones that are the same. So the angles that are across from them have to be the same as well. So in this case, we would refer to angle F and angle G as the congruent angles. So segment FG would be the base of the triangle, and point H would be the vertex of the triangle. So let's talk a little bit about equilateral triangles. Obviously, if they're equilateral, all the sides are the same. But if all the sides are the same, that means that all the angles across from them have to be the same as well. So just make sure that you understand, an equilateral triangle is considered isosceles as well, because the definition of isosceles says that it has to have at least two sides that are the same. Well, equilateral triangles fit that description, so equilateral triangles are also considered isosceles. Now, equilateral triangles are going to play a part in future lessons also, particularly when we're talking about special right triangles and a little bit when we're talking about regular polygons. But for the time being, just recognize that all the sides and all the angles are the same. So why are all the angles the same? So what are the measurements of angle RS and T in example 2? Well, if we don't know what they are, we can just call them X. But because the sides across from each angle are the same, we'll call them X all the time because they have to be the same thing. So if we substitute X into a problem, we would be able to say that 3x is equal to 180 degrees, and if I divide out three sides, or if I divide 180 by 3, that shows us that each angle measurement inside of an equilateral triangle would be 60 degrees. Now here, this is a really nice example. I like the fact that they're using more than one type of triangle in the figure, and we're having some things overlapping. So let me just illustrate what I'm looking at here. One of the things that I like. So first of all, it does say, well, let's just find the values of x and y. How do we do that? So again, just for the time being, pretend that the solution stuff isn't there. Let's just look at the figure because, when you have to do an assignment or quiz or test, well, they're not going to give you all of that stuff to just fill in the blanks with. It's just, think about it and see what we get. Well, here, and here, what I'm looking at on those three angles, I'm seeing that those three angles are the same. So because those three angles are the same, it means triangle JKL must be isosceles. I'm sorry, not isosceles, but equilateral. So if all of the sides are the same, then that means x has to be equal to 8. Well, one of the other things that we notice, let me pick another color here. Here in triangle JML, we have a pair of congruent angles. So that means triangle JML has to be an isosceles according to the converse of the base angles theorem. So that means segment JL and segment ML have to be the same. So if JL is 8, ML also has to be 8, so we can say 2y has to equal 8, divide both sides by 2, and that's how we get 4. So now let's see, taking that information into account after we've already thought our way through the problem, how can we fill in the blanks? So again, we know that it's going to be equiangular because they were given to us that way. So if it's equiangular, it's also equilateral. So that means KL and JL are congruent, so that means X is 8, which we already figured out. So now we have JML and MJL. Those are congruent to each other. So the two sides that are the same in the isosceles triangle, LM and LJ. So LJ has to equal 8, so then we just substitute and solve for X. Now again, here's another example that I really do like for a couple of reasons. One, it's going to be incorporating concepts that were used earlier in earlier lessons of this topic, but it's also just making you think, well, what do I know? What do I know about this figure, and what can I figure out without assuming that it's going to be true because it looks that way? So here we have a quilting pattern. Explain why triangle ADC must be equilateral. So let's look at triangle ADC for a second. So oops, let me ADC. We want to know, why is that going to be the same? Well, clearly it must be isosceles because I do have two sides that are the same. But the sides that are the same aren't opposite of the angles that are marked on the figure. So looking at the angle located at point A, since the side across from it is the same as the side across, okay, let me start over. From point A, the angle that's marked there, the side across from it is segment CD. Because that segment CD is the same as segment AD, it must mean that the angle here at C also must be the same as the angle at point A. And clearly, if all of the angles are the same, all of the sides must be the same. So that is what is going to tell me triangle ADC must be an equilateral triangle. So the second part says, show that triangle CBA is congruent to triangle ADC. Okay, so let me pick another color here. So CBA. Now we're going to look at this blue triangle. Why is that blue triangle and the red triangle, why are they going to be the same? Well, looking at segment AB, we can see that it's the same length as segment AC, so it's definitely at least isosceles. So if the blue triangle is isosceles, at least, then angle B has to be the same as angle here at point C. So looking at the figures, we can at least see that I have, let's see, an angle, and a side here, and I can find the corresponding angle, and side on the red triangle. So I can justify that the two triangles have to be congruent to each other using the angle side congruence theorem. So again, like I said, I like it because it makes you think about the properties of the figures, and it does incorporate things that we have used in previous lessons in this topic. So here, this is pretty much where we're going to wrap it up. I want you to pause the video and try answering these three questions on your own. And when you're ready, come back and compare your answers against mine. Okay, so let's look at the figure. Copy and complete the statement. So you don't need to copy the statement, just complete it. So if FH is congruent to FJ, so if this and this are the same, well, what angles have to be congruent to each other? Well, if those two segments are the same, it would make triangle FHJ congruent to each other. I'm sorry, not congruent. It would make it an isosceles triangle. So segment HJ would be the base. So angle H and angle J would have to be the angles that are congruent to each other in that isosceles triangle. So if triangle FGK is equiangular, well, let's go ahead and mark that. Let me pick a different color here. So if it's equiangular, we'll just mark them equiangular. Then segment FG is 15. Well, if it's equiangular, it must also be equilateral. So if FG is 15, GK also has to be 15. Now you're going to have to go back and look at the other diagram in figure 3, I'm sorry, in example 4 to see what is the measurement of angle. Use the parts to show that the measurement of angle BAD is 120 degrees. Well, if we just go back for just a second, well, BAD, let me pick another color here. So BAD is this angle right here. Well, what we have showed in this example is that the two triangles, the one in red and the one in blue, were both equilateral. So that means angle BAC and angle DAC are both 60, so together they make angle BAD, which makes it 120. So that's what I'm using as an explanation in my answer for part 3. So again, properties of isosceles and equilateral triangles, they are going to be very useful. You will see them again in future lessons. Isosceles triangles, two sides are the same, two angles also the same. That's something that a lot of students don't quite, that's something that you generally pick up in high school geometry. Equilateral triangles, obviously, they're all the same, but that's pretty much it as far as equilateral and isosceles triangles are concerned for what we're going to be using with them right now. So as always, guys, if you have any questions about anything that you've seen in this lesson, make sure that you send me an email, leave me a comment in the class. But until next time, guys, thanks for watching and take care.